Halfway through August, a single number came back from the buoys and satellites monitoring the tropical Pacific Ocean that made climate scientists sit up in a way they hadn't all summer. 2.7 degrees Celsius above normal. That's not just deep into Super El Niño territory. That's a number that, at this exact point in the calendar, has already blown past where the last Super El Niño, the historic 2015 to 2016 event, was sitting at its absolute peak, not matched it, exceeded it. Months before this year's event is even expected to reach its own maximum strength. Something scientists were tracking cautiously back in the spring has, over the last few weeks, turned into one of the fastest intensifying El Niño events ever recorded. And the ripple effects are already showing up in places nobody was necessarily expecting this early. From a quietly shrinking Atlantic hurricane forecast to an entirely separate ocean basin on the other side of the planet suddenly warming in lockstep. And for California specifically, a state already bracing for what this event could mean for its coastline and its winter storm season, this acceleration changes the calculus in ways worth understanding in detail. Today, we're breaking down exactly what just happened in the tropical Pacific, why the pace of this event has genuinely surprised the scientists tracking it, what a second, less talked about, ocean pattern developing at the exact same time means for how this whole thing plays out, and exactly why California, more than almost anywhere else in the country, has real reason to be paying close attention right now. Straight from the latest ocean temperature data, the World Meteorological Organization's own seasonal outlooks, and the researchers tracking this event daily. If you want the next update the moment this event's trajectory shifts again, get subscribed and turn on notifications right now. Let's get into it. Let's start with the number that changed everything, because understanding exactly how it's measured is the key to understanding why scientists reacted the way they did. When climate scientists talk about El Niño's strength, they're referring to the surface temperature of a specific, closely monitored patch of the central and eastern tropical Pacific Ocean, an area meteorologists refer to using the shorthand Niño 3.4. Under normal neutral conditions, that patch of ocean sits at a fairly stable baseline temperature. During an El Niño event, it warms above that baseline, and the further above baseline it climbs, the stronger the event is classified. A genuine Super El Niño, the rarest and most extreme tier this classification system has, requires that region to sustain a warming anomaly of at least 2 full degrees Celsius above normal, sustained over a period of months, not just a brief spike. According to the International Research Institute for Climate and Society at Columbia University, which tracks this index continuously using an ensemble of 26 separate forecasting models, the seasonal average for May through July of this year already reached 1.51 degrees Celsius above normal. That alone would represent a solidly strong El Niño by historical standards. But the trajectory from there is what actually matters here. The monthly value for July alone climbed to 2.03 degrees, crossing the formal Super El Niño threshold outright. And then, in the very latest weekly reading, centered on August the 12th, that number climbed again, this time reaching 2.7 degrees Celsius above normal. Every single one of those numbers represents an acceleration from the reading before it. And forecasters at the World Meteorological Organization now expect the seasonal average anomaly across August through October to exceed 2.9 degrees Celsius in the core monitoring region, a genuinely extreme reading by any historical comparison. Here's the part that actually earns this story its shocking turn framing. Researchers tracking this event have directly compared its current development against the 2 most significant El Niño events in the modern satellite record. The powerful 1997 to 1998 event, and the more recent 2015 to 2016 Super El Niño, the last time the world experienced anything in the same extreme category. When you plot this year's trajectory against those 2 historical events on the same calendar timeline, this year's event has already surpassed where the 2015 to 2016 Super El Niño was sitting at its own absolute peak strength, months before that comparison point in the season. In other words, the strongest El Niño most people currently alive have any real memory of, the one that dominated global weather headlines throughout the winter of 2015 into 2016, had not yet reached the intensity this year's event has already achieved, and this year's event isn't even expected to hit its own peak until later in the fall or winter. Researchers studying the event have explicitly noted that its current pace of development is unusually rapid compared to essentially every other Super El Niño event available in the historical record. To understand why this event is developing so much faster than its predecessors, you have to look beneath the ocean surface, literally. Researchers monitoring ocean heat content down to a depth of roughly 300 meters, nearly 1,000 feet beneath the surface, have documented a rapidly expanding pool of unusually warm water spreading across the tropical Pacific since spring, driven by a specific atmospheric phenomenon called westerly wind bursts. Under normal conditions, steady trade winds blow from east to west across the tropical Pacific. effectively piling up warm surface water on the western side of the ocean basin, near Indonesia and the Philippines, while allowing cooler water to well up from the deep ocean along the eastern side near South America. A westerly wind burst is a sudden temporary reversal of that pattern, a pulse of wind blowing the opposite direction, west to east, strong enough to push a wave of unusually warm subsurface water, technically called a Kelvin wave, rolling eastward across the Pacific toward South America. When these bursts happen repeatedly and with enough intensity, they don't just create a temporary warm pulse. They can fundamentally destabilize the ocean's normal temperature structure and kick off a self-reinforcing warming cycle that is exactly what meteorologists watch for as the telltale sign of a developing El Niño. This year, those westerly wind bursts have been arriving with unusual frequency and strength since spring, and forecasters are projecting the pattern to continue and even intensify further through August, meaning the engine driving this event's rapid growth shows no signs of running out of fuel anytime soon. There's a second piece to this story that hasn't gotten nearly as much attention as the Pacific warming itself, and it's exactly the kind of development that qualifies as a genuine surprise twist in how this year's climate pattern is shaping up. On the completely opposite side of the world, in the Indian Ocean, a separate but related climate pattern called the Indian Ocean Dipole has been quietly developing in lockstep with the Pacific event. The Indian Ocean Dipole describes a temperature seesaw across the Indian Ocean basin, where the western half, near the coast of East Africa, becomes unusually warm while the eastern half, near Indonesia and Australia, becomes unusually cool, or, in this case, the pattern is shaping up as what scientists call a positive dipole event. According to the latest forecasts from multiple international modeling centers, that positive Indian Ocean dipole is now expected to strengthen significantly and remain firmly established from September through December of this year, developing at almost exactly the same time as the Pacific's Super El Niño reaches its own peak intensity. Why does that matter? Because El Niño and a positive Indian Ocean dipole, while technically distinct climate phenomena occurring in two entirely different ocean basins, are well documented to reinforce and amplify each other's effects when they occur simultaneously, a pattern scientists have observed and studied in previous years when the two have aligned. Individually, either pattern is capable of shifting global rainfall and temperature patterns in significant ways. Together, occurring at full strength at the same time, their combined effect on global weather becomes considerably harder to predict using simple historical comparisons, precisely because most of the reference events scientists typically compare against didn't feature both patterns peaking simultaneously at this kind of extreme intensity. The World Meteorological Organization has been direct about the practical consequence of this pairing, warning that the combination substantially raises the risk of drought, flooding, and wildfire activity across a wide swath of the globe, with the region surrounding the Indian Ocean basin specifically flagged as facing amplified impact from having both patterns working in tandem. This is precisely the kind of development that's leading forecasters to describe this event using language considerably more cautious than a simple, confident prediction. NOAA's own August hurricane outlook, discussing the same developing Super El Niño, included a genuinely notable piece of institutional humility, stating plainly that a strong event like this one could produce different impacts than those traditionally observed in past El Niño events, rather than simply a stronger version of the same familiar effects. That's a meaningfully different statement than saying this year will simply be a bigger repeat of 2015 or 1997 or 1982. It's an acknowledgement from the government's own primary forecasting agency that the unusual combination of factors driving this particular event, its record-breaking pace of intensification, its pairing with a simultaneously strengthening Indian Ocean dipole, and the fact that it's developing against an already historically warm global baseline, means the standard playbook scientists normally use to project an El Niño's downstream effects may not translate cleanly this time around. There's already tangible, real-world evidence of this event's influence showing up in places entirely disconnected from California or the Pacific Ocean, which is worth walking through briefly because it demonstrates just how far-reaching El Niño's atmospheric fingerprint actually extends. NOAA's August update to its Atlantic hurricane season forecast reduced its projected storm totals for the second time this year, now calling for somewhere between 7 and 13 named storms and just 2 to 6 hurricanes, with as few as 0 major hurricanes expected this entire season. That's a meaningfully quieter season than the already below-average forecast issued back in May, and the mechanism behind that suppression comes directly from El Niño itself. Strong El Niño events reliably increase wind shear, the difference in wind speed and direction at different altitudes across the tropical Atlantic, and that increased shear tends to tear apart developing tropical systems before they can organize into genuine hurricanes. Colorado State University's own August outlook, from the team that pioneered early season hurricane forecasting back in 1984, independently arrived at a similarly suppressed forecast, further reinforcing just how directly and immediately this Pacific Ocean event is already reshaping weather patterns on the completely opposite side of the North American continent months before its own peak strength has even been reached. Now let's bring this all the way back to California. Because everything we've just covered, the record pace of intensification, the simultaneous Indian Ocean dipole, the genuine scientific uncertainty about how this specific combination behaves, feeds directly into why the state has real, concrete reasons for concern heading into the coming winter. The most immediate and measurable threat is sea level. Strong El Niño events physically raise coastal sea levels along the west, coast through a combination of thermal expansion, since warmer water simply occupies more physical volume than cooler water, and a phenomenon called coastally trapped waves, where the altered wind and pressure patterns associated with El Niño push additional ocean water directly up against the California coastline. Climate researchers tracking this event have estimated that a super El Niño of this magnitude could produce a temporary sea level rise along California's coast in the range of 6 to 10 inches above normal. That figure doesn't exist in isolation. It stacks directly on top of the roughly 6 inches to a foot of permanent sea level rise California's coastline has already experienced over the past century due to broader climate change, with the precise figure varying by location along the coast. Combine a temporary El Niño-driven surge running at the higher end of that 6 to 10 inch range, now made considerably more plausible given how much faster and stronger this event is developing compared to earlier projections. With a century of already accumulated permanent sea level rise, and California is looking at a genuine, credible possibility of recording its highest coastal sea levels ever measured at some point this winter. And that's not a distant abstract projection either. Bay Area sea levels had already climbed by roughly half a foot earlier this year, well before this event's recent acceleration, partly attributable to the ocean warming already underway, even before the Niño 3.4 index crossed into full super El Niño territory. With the event now developing considerably faster and reaching considerably higher intensity than earlier forecasts suggested back in the spring, the upper end of those sea level projections has become meaningfully more likely rather than less, precisely the kind of shift in risk calculus that this month's rapid intensification directly drives home. Coastal communities up, and down the state should reasonably expect an elevated risk of dangerous wave events and coastal flooding, particularly during king tide periods when normal tidal cycles already push water levels higher than average, and particularly in low-lying areas around San Francisco Bay, along the Santa Cruz coastline, and through Southern California's beach communities, all of which have experienced flooding and erosion during previous, considerably less extreme El Niño winters. The second major California-specific concern tied to this event is the state's winter storm season, and specifically the atmospheric rivers responsible for delivering a substantial share of California's annual water supply in concentrated, sometimes destructive bursts. It's worth being precise about this relationship rather than oversimplifying it, because a strong El Niño doesn't automatically guarantee a nonstop parade of storms marching into the state. What an event of this magnitude does is meaningfully shift the underlying odds toward a wetter than average outcome, particularly across Southern California. And for an event reaching the kind of extreme intensity current data now suggests, those elevated odds likely extend into Northern California as well. The mechanism driving that shift runs through the jet stream, the fast-moving current of air high in the atmosphere, responsible for steering storm systems across the Pacific toward the west coast. In the very strongest El Niño events on record, both the polar jet stream and a separate current called the subtropical jet stream can intensify and align simultaneously, creating exactly the kind of atmospheric configuration capable of driving repeated, powerful storms directly into California over a sustained stretch of the winter, rather than the more scattered, unpredictable storm pattern typical of a weaker or more neutral year. Given that this year's event has already exceeded the pace and intensity of the last Super El Niño at a comparable point in its development, the conditions required for that dual jet stream alignment appear meaningfully more likely to actually materialize this winter than they did during more moderate historical comparisons. There's a third layer to California's exposure this particular year that makes the state's situation genuinely more complicated than a typical El Niño winter, and it involves water sitting much closer to the California coastline itself, rather than out near the equator where El Niño technically originates. For 7 consecutive years now, California's coastal waters have experienced a recurring series of marine heat waves, periods of anomalously warm water sitting directly along the state's own shoreline, entirely separate from and closer to shore than El Niño's warming footprint out in the tropical Pacific. The most notorious of these coastal marine heat waves, an event scientists nicknamed the Blob, struck between 2014 and 2016, arriving at almost exactly the same time as the previous major Super L. Niño and the combination triggered unprecedented toxic algal blooms along the California coast, forcing the closure of entire commercial and recreational shellfish harvesting seasons and disrupting fisheries up and down the state, with the fresh marine heat wave already active along California's coastline as this new, faster developing Super El Niño continues intensifying out in the broader Pacific. Scientists are watching closely for a very similar compounding effect. Two independent sources of ocean warming, one originating locally along the coast and one originating thousands of miles away near the equator, layering directly on top of each other along the exact same stretch of California coastline at almost exactly the same time. That layered warming carries real consequences for the marine ecosystems California's coastal economy depends on. El Niño conditions reliably disrupt the cold, nutrient-rich upwelling that normally rises from the deep ocean along the California coast, a process that forms the literal foundation of the entire regional marine food chain, supporting everything from anchovies and sardines up through the state's commercial and recreational fishing industries. Marine biologists tracking these shifts have described the resulting change in blunt terms. A strong El Niño effectively creates a completely different ocean off the California coast, one where species like squid, anchovies, and sardines get pushed considerably further north than usual, chasing the cooler water conditions they actually need to survive. That kind of shift in prey distribution has historically coincided with more frequent sightings of warmer water predator species along the California coastline during past strong El Niño winters, including hammerhead, tiger, and bull sharks, species not typically associated with California's normally cooler coastal waters under neutral conditions. It's genuinely important to be honest about the limits of what any of this data can actually predict with confidence, because that honesty is exactly what separates a responsible breakdown of this story from manufactured climate alarm. El Niño's downstream effects have never played out identically from one event to the next, even among the small handful of previous Super El Niño events scientists have on record. The 1982 to 1983 event caused catastrophic flooding in Peru so severe that some rivers there were reported carrying roughly 1,000 times their normal flow, while producing a comparatively different set of impacts across North America. The 2015 to 2016 event, meanwhile, coincided with a severe, devastating drought across Ethiopia, an almost opposite regional outcome despite both events originating from the same broad global climate pattern and both reaching genuine Super El Niño intensity. Climate researchers discussing this year's event on public radio have even drawn comparisons to the historic El Niño of 1877 and 1878, an event now recognized among climate historians as one of the deadliest climate disasters in recorded history, associated with catastrophic famines across multiple continents simultaneously. Raising that comparison isn't meant to suggest this year's event will replicate that specific historical catastrophe. It's meant to underscore how dramatically a Super El Niño's actual downstream effects can vary by region and by the specific atmospheric conditions it happens to interact with, even when the underlying strength of the event itself is confidently expected to be historic. That variability is exactly why the genuinely new information from this month, the unusually rapid pace of intensification, the simultaneous strengthening of the Indian Ocean dipole, and NOAA's own explicit acknowledgement that this event could behave differently than past comparisons would suggest, matters so much for how seriously this story deserves to be taken heading into fall and winter. This isn't simply a case of a well-understood, thoroughly studied phenomenon happening, to arrive at a slightly larger scale than usual. It's a genuinely novel combination of factors, developing faster than historical precedent, pairing with a second ocean basin's climate pattern in a way that amplifies uncertainty rather than resolving it, and unfolding against a global baseline temperature that's already historically elevated before this event even began adding its own warming on top. Scientists tracking this event are being unusually direct about exactly how much genuine uncertainty remains, in translating all of that into a confident, specific forecast for any single region, California included. So what does all of this actually mean for anyone living in California right now, watching this event continue to intensify faster than anyone expected back in the spring? The practical guidance doesn't require waiting for perfect certainty about exactly how severe this winter ultimately turns out to be, because the range of plausible outcomes this event now supports skews meaningfully toward the more extreme end of what California's emergency planners already prepare for during a typical El Niño year. Coastal residents, particularly anyone in a low-lying area with a history of king tide flooding, should review their flood. Insurance coverage now, well before storm season is actually underway, since standard homeowners insurance typically excludes flood damage entirely, and separate flood insurance policies usually carry a waiting period before coverage actually takes effect. Anyone living near the coast should take the time now to understand their property's specific flood risk profile, since this event's temporary sea level boost, especially if it lands toward the higher end of the 6 to 10 inch range, now looking more plausible given the accelerated pace of development, could turn a previously minor, occasional nuisance flood into something considerably more serious and more frequent throughout the winter months. Central Valley agricultural operations, already watching this event's development closely given how directly California's water supply depends on winter precipitation, should factor the increased likelihood of a wetter than average season into planning around drainage, flood risk to low-lying farmland, and water storage decisions heading into fall. For residents in areas scarred by recent wildfires, where vegetation loss leaves hillsides significantly more vulnerable to catastrophic failure even in rainfall totals that wouldn't threaten an undisturbed slope, the elevated odds of a stormier than average winter deserve particularly close attention, since debris flows and landslides in burn scar areas have historically caused some of the most severe sudden loss of life during past strong El Niño winters in California. Anyone in that kind of high-risk terrain should pay close attention to evacuation guidance the moment atmospheric river storms actually begin arriving, rather than assuming a structure or hillside that held up fine in previous years will necessarily behave the same way under this winter's specific conditions. There's a broader lesson embedded in this entire story that extends well beyond just this one climate event, and it's worth sitting with before wrapping up. The genuinely responsible way to cover a developing climate pattern like this one isn't to pick a single dramatic headline number and run with it as though the outcome is already certain. And it also isn't to dismiss real, measurable acceleration in the underlying data simply because long-range forecasting always carries some inherent uncertainty. It's to walk through exactly what the data actually shows, be honest about where genuine scientific consensus exists and where real acknowledged uncertainty remains, and let people understand the actual range of plausible outcomes rather than either a manufactured worst case or a falsely reassuring best case. What we know with real confidence right now is that this event has developed faster and reached a higher intensity earlier in the season than any previous Super El Niño in the modern record, that it's now pairing with a second, independently strengthening ocean pattern in the Indian Ocean, in a way that compounds rather than resolves the uncertainty around its downstream effects, and that its influence is already measurably reshaping weather patterns as far away as the Atlantic hurricane season, months before its own expected peak. What remains genuinely uncertain is exactly how severe California's winter turns out to be, exactly how high sea levels ultimately climb at any specific stretch of coastline, and exactly which of the historical comparisons, if any, this year's event ends up most closely resembling once it's finally run its course. For California specifically, the honest bottom line is this: the state was already bracing for a potentially historic winter based on data available back in early August, and the acceleration recorded since then has, if anything, made them more severe, and to those earlier projections, meaningfully more plausible rather than less. That's not a reason for panic, but it is a genuinely credible reason to treat this winter's preparation with real seriousness, rather than defaulting to whatever a typical California winter has looked like in years without an event of this magnitude developing in the background. We'll be tracking this event's continued development closely as it heads toward its expected peak later this fall, along with every update on the Indian Ocean dipole's own trajectory and what both patterns together end up meaning for California's actual winter storm season once it finally arrives. Subscribe and turn on notifications so you don't miss the next update the moment new data comes in on either front. Drop a comment and let us know if you're in California and how seriously you're taking this year's preparations compared to previous winters. And if this gave you the real detailed science behind the headlines instead of just another alarming climate story, hit like and share it with someone who needs to see it. Stay prepared, and we'll see you in the next one.